talk on convergence for adaptive resampling of random features.
Thank you. It is a joint result with Xin Huang, Kammonen, Anamika Pandey, Mattias Sandberg, Erik von Schwerin, and Raul Tempone. I will first give you an experiment of adaptive random features, and then background on random features from the beginning, and what is the adaptive random features now, and then some numerical results. The starting point is these numerical results by Kammonen, Pandey, von Schwerin, and Tempone in an archive paper where they simulate with random features with resampling. And that is here we have the training error of that, and here we have the testing error. And here is a standard Adam method applied to a problem in dimension 4. And in one dimension, the function is almost a jump and has oscillations like this. And what we see is the generalization, the mean square error here on this axis, and computational time here. So the talk is about to try to understand why does it do like this, and why, so the talk is about understanding these curves. So then we come to the background. What are random features? Suppose you are given data where x is in dimension d and y is in R in dimension 1. And we have capital J of this data, and we assume that the data y is a function of x with some noise here, independent with mean 0, and variance is squared. So the sample points, they are identically independent samples, and they are also independent from the noise. That is the setting. And the random feature is about finding an approximation to this function f. And then theoretically, what do we want to have? We want to have a representation that we can represent the function like this, for instance, with a Fourier transform, so that the function f can be represented with its Fourier transform. If we have then we are led to Fourier feature, random Fourier features with this activation function, the complex exponential. If we would have another activation function, we would need to have another representation. That has also been tested with this resampling method, but I will not talk about that today. So here comes the training setup. You take the data point and the neural network beta. So beta is this function. You have some amplitudes and the complex exponential for the activation function. And you have capital K amplitudes and K frequencies. And you want to minimize the mean square error, and with a positive parameter lambda here, thicken up regularization. And here you have the L2 sum of the amplitudes. The random features, the name random comes from that the frequencies omega, they are independent samples from a density P. And the whole issue is how to choose this density P. That's the first step that we want to understand. What is a good choice? And then the next step is, can we obtain independent samples from this density or an approximation of it? In a way, this is what resampling does and gives this curve. And we will try to explain why this happens here. So the first thing, how should the density be? Where does it come from? If we simplify the setting so that we have infinite amount of data and no noise, then the mean square error can be derived quite easily, and I will do that soon. And it has a first step that you, instead of looking on the minimum over taking minimum over omegas, you take the minimum over amplitudes given an approximation of sampling omega from a density. Then one do some steps and one obtain an estimate of the error, the generalization error estimate. This is standard, and it is the way we will understand the convergence of this resampling random feature method. So our next goal is to see how should we choose P in order to minimize this constant that comes up here. That is our main goal now. So we need to derive this error estimate, and it has two steps. They're quite straightforward. The first step is to do a Monte Carlo approximation of the Fourier representation, and then plug in this result into the minimization problem. So we assumed we have a representation of the function by its Fourier transform, and then we do a Monte Carlo approximation of this integral by sampling the frequencies omega from independent from a density P. Then we have this expression as sum, and we have capital K of these samples omega. And we denote this is now a neural network, and we denote this neural network by alpha. And note first that the expected value of the neural network is precisely the integral, so that there is no bias. The error will then be determined by the variance, and here is the variance. So we try to compute the variance, and we take so here is so we use the representation we have of the neural network. That is the representation, and we square that representation. This is squared here and summed here. So we have this square, and now by the independence of the frequencies, the double sum here becomes a single sum, and with these terms in the single sum, and that gives, this is the estimate we have. So this constant here that I mentioned before, CPF, that is what we have obtained here. the Fourier transform, expected value of the Fourier transform divided by the density squared. So one see that the constant will be very large if we don't sample well here, so that if we sample very few omegas where their frequencies actually appear, then we will have a big constant. And the estimate we have is then that the generalization error, this is going to be less than if we plug in this Monte Carlo approximation I just derived. So we plug that in here. We replace the neural network with the Fourier representation neural network from Monte Carlo, and then we obtain from this term we obtain 1 over k and the 1 here and this, and it turns out if you compute out the lambda term you get the same thing here. So this is the estimate we have, and the constant, as I mentioned, is here, the constant depending on the function and how we sample. The idea of the resampling method is now to choose p so that we have as small constant as possible. So let us see what happens then. So we want to minimize the constant, this constant, by choosing a good value of the sampling density p. So then you just compute, you do a perturbation of p by a function that has integral 0, and then you take the derivative with respect to a multiple of that function, and you get this one divided by p squared and a minus times the function that has integral 0. So that means that p squared f hat squared divided by p squared need to be constant, so that p has to be proportional to the Fourier transform amplitude absolute value, and the integral has to be 1, so that we have derived the minimal value of the constant. The goal is then to estimate, find a method that finds this density approximately, although we don't have access directly to the Fourier transform. That's the goal now. And here is a result, theoretical result on that. So we will first look on the case where we have infinite amount of data, but finite amount of nodes and frequencies. So the starting point is that we take a density p, which doesn't have to be optimal, but it is not totally bad. So we assume something. So we assume that it samples basically all frequencies. So that is an assumption, but the constant can be big here. So that is an assumption. We have an initial density p that has this quotient bounded, so that all frequencies that are in some way that we need, they will be sampled. And then we need an assumption of the Fourier transform amplitudes, that they are bounded in this way. We have a constant, and we will look on a bounded domain, so that we use a Fourier series instead of a Fourier transform representation. So then the the frequencies omega are pi over some lengths in the periodic domain times a value n representing lattice point in CD. And we also need a lower bound of the Fourier transform in our proof. And we need a cutoff parameter, which depends on the number of nodes, so that the cutoff goes to 0 when the number of nodes go to infinity. And then we have a number q that is basically the square root of the cutoff epsilon, which is small also and goes to 0 as we take infinite number of nodes. So then with this parameter set, we now sample, we want to do the resampling. What does the resampling mean? The resampling means to sample many frequencies, k times 1 minus q, so q is small, so approximately k frequencies. We are going to sample from a density proportional to the amplitudes of the neural network that we have obtained here with this density p. And then we will again sample from p, a few of them, and so that we add up to capital K. The remaining one comes from this density p here. With this setup, we form a new neural network, alpha bar, the resampled neural network. And that then has an estimate here that we will prove. So the generalization error is bounded as before. And what appears now is the optimal constant here, the optiminimal constant, and something that tends to 0 when the number of nodes goes to infinity. So in this way, we mean that in some sense, the first figure I showed, what we have here is related to that bound when we have 1024 nodes. Here we have iterated the resampling, and that I will come back to that. And that is because this estimate here, suppose you initially don't have this bound, then one can do a random walk in the frequencies and to gradually increase, and I will come back to that. But our goal now is to understand how can one prove this estimate. Okay, so as I said, our method will be based on looking on the constant for the resampling method, the CPF. And to simplify the analysis, we'll use Fourier series instead of Fourier transform. And the first important step, that is to be able to handle the amplitudes of the neural network and derive that equal amplitude property that I will explain. And then we will also see that we need to cut off small amplitudes, because we will always have, when we do finitely many nodes, we will have an error in and the small amplitudes will be polluted more by this error. So to do an estimate, we will need to cut off small amplitudes. They don't contribute much to the neural network, but they the error in the amplitude is large, so the normalization here will be uncontrolled. So here we actually have the cutoff here. I didn't mention that before, but one need to cut off. One cannot normalize by all amplitudes in the proof. One need to cut off amplitudes that are small. That is an important part. Okay. Now the first step, then what is the equal amplitude property? So suppose we denote by beta bar the sum of the amplitudes with a given frequency omega n. So in the neural network, we have a nu k, and then we sum all these that have this given frequency omega n. So these are the amplitudes corresponding to the same basis function. They have the property that actually the amplitudes are equal. And this is because we have the penalty in the minimization. Here we minimize this, so we have this penalty, and the neural network, of course, when we fix the basis function, we get the sum of, for one basis function, the sum over all amplitudes for that basis function. That is what we have here. And the least squares problem in the first term here, that only see the sum, namely this, it only sees this constraint that the sum is equal to that. And then in the formulation, one need to minimize the square norm here, and that is minimized when they are equal. So now we know that all of these are equal. And therefore, if we sample with a density proportional to the amplitudes like this, it will be the same as sampling with the density related to the basis functions. And that is a bit fantastic in a way, because the amplitudes, we are taking the absolute value of the amplitude, so we don't, we have, it's not easy to prove, I mean, strong convergence and such things of these properties of the amplitudes. We would typically expect weak convergence, but here we can get convergence of the absolute value in some sense, because this that they are equal. So now sampling from what we have in practice will be the same as sampling from what one wants in theory, where for each lattice point one would like to have this density. So why do one want that density? That will be described soon in the proof, but suppose first that we so that it is consistent, that we have infinite number of nodes and data points, then the neural network will be equal to the intended function, and we have this Fourier series representation. So if we compute the Fourier coefficient for based on this function, then we see that the neural network, the sum of the amplitudes for that Fourier related to this Fourier coefficient would be this beta bar. So we will have here we see that we obtain the right Fourier coefficients in the neural network in the limit, so that it is consistent. And we in some way see that at least in the limit it is optimal. So here one could think, how should one now prove convergence? In the literature around resampling, one typically look on the density, how does the density converge and so on. That seems difficult here because the least squares problem determining the amplitude couples the frequencies in a complicated way. So the proof is different. It just looks on the constant, as I mentioned. It just looks on how does this constant CP evolve. Okay, so here are some, I will soon describe the theoretical result, the proof a little bit, but first some numerical results. So what does it do, the resampling algorithm? You have some input data and you want to form a neural network like this. And what do? You choose, now we will have to iterate. So you choose a number of iterations for the resampling and a step size for random walk and a Ticken or parameter value lambda. And we set the initial frequencies to 0, and then we sample standard normal distributed independent numbers, zeta, and we do a random walk with the step size delta. So now we don't have 0 anymore. We have amplitudes which are described by this standard normal times delta. Then when we have these amplitudes, then when we have these frequencies, I mean, then we can solve the least squares problem for the neural network and we obtain the amplitudes. Okay, then given the amplitudes, then we can resample in the way I mentioned, so that we resample the amplitudes from this density. And it could be with cutoff and without cutoff. So numerically, we have tested both. Theoretically, we need cutoff, but in practice, I will show you we don't need a cutoff. So one resample the frequencies based on this probability density, and then one iterate this capital N number of times and end up with a neural network in the end. So here is the result from a simple model problem. So we have a exponential like this scaled with a, so what is important is the Fourier transform of this function. So in one dimension, it is exponential with a small parameter a here. And in the other, it is Gaussian, standard normal. We are now in dimension 2 to be able to plot here. And we have chosen some parameters of the penalty and so on. And here we have 15,000 data points and related number of nodes. So the distribution of the frequencies in one direction corresponding to not being in this direction V here, then one have standard normal in this direction, and this is around you see 3, 4 here frequencies number, and then in the other direction it's much bigger, 60. So the Fourier transform of this is related to the Cauchy distribution, which decays slowly, 1 over 1 plus omega squared. And so here is this function in dimension 1 this function here is a step. I mean, it is like a point mass, but the integral is not 1, but is a and then the initial start for the resampling method is standard normal. And then here we have the convergence, mean square arrow going down. And here we have the iterations. And here is the final frequency distribution. And then we compare here with the optimal. So here is in the direction where it is standard normal. And then you see the red curve is the optimal distribution, and the blue histogram is what we have sampled. And then in the other direction, with this direction of the spike here, the frequency is much bigger, you see, up to 60, and the iterations have not been the decay here is slow. I mean, it doesn't even have a mean, so it is slow, and therefore difficult to find this. But those that have not been iterated, they are still here. But anyway, it is closely finding the most important frequencies. So this is after a number of iterations, 100 resample iterations. If one stop after 50, then one see that one have not, then it is already here at 20 frequency. The frequency is around 20, and from iteration 15 to 100, it increases up here to 60. Okay, so let us now see how the theoretical understanding of this result goes. So as I have mentioned, we want to study the constant, which is related to the Fourier transform divided by the density. And the first step is to have a representation of the error and then use the cutoff. So what we want to estimate is the generalization error here. We have the neural network, the resampled. We have first done one step with the sampling P, so that we have some amplitudes, and then they are sampling with the density P, and then we have some other frequencies that are sampled from the resampling density. Okay, so this function alpha bar has this combination of the two in the theorem. So you remember here some frequencies from the original, a few of them, k times q, they are from the original, and then the remaining, many of them, asymptotically k, they are from the resampled. Okay, so then what do? We split up the function f into two parts. One, because of the cutoff. So one, we cut off the high frequency part and call the cutoff function f epsilon. So here are the low frequency with the amplitudes bigger than epsilon. And here are the amplitudes, the remaining, with smaller than epsilon. And the resampling that we put, that estimates now this bound, the generalization is bounded by is smaller than taking the resampling only on the larger amplitudes, non-cut off, and then the remaining with the original density, non-optimal density, that samples all frequencies only not with an optimal constant, but this function itself will have a small norm, the difference here. That's the idea. So then we have two terms, R1 corresponding to the error here, and R2 corresponding to the error there. And let us now see how we do this estimate. So for the first term, that is with the large amplitudes here, the large amplitudes. So then, and we are sampling with here is the resampling density. So then we know that the error will be the number of nodes, which is now k times 1 minus q, 1 over that, plus 1 plus lambda, and times the density, the estimate of the CP, and it is the Fourier transform square divided by the density. And now this resampling density depends on the amplitudes which are sampled from based on the frequencies related to p. So that is the what we need to estimate. How big is this number? Then what we see here is actually nothing has happened. We are just plugged in the density p bar. This is beta bar divided by the sum of beta bar, and so we have just replaced here what p bar is. It is this density. Okay, so now we need to know something about the error in the amplitudes, and we know with the original sampling from the density p that the difference of the neural network and the function, that decays like 1 over k in the generalization error. And if we use that to estimate the Fourier coefficient related to the difference, that estimate gives the Fourier coefficient decays like 1 over square root of k for all frequencies. Okay, so that is important to know. Then we split up the error. What we have, this error, we split it up into two parts. One, when it happens, this event that the Fourier coefficient is small enough, namely epsilon over 2. So let us look on this case first, this event when the Fourier amplitude is less than epsilon over 2. Then what we have here is f divided by beta, but beta bar, this is f hat plus the error eta, the error eta of the Fourier coefficient. So when we know that the amplitude is bigger than epsilon, so that is here, but we have this square here. One of them we write like f plus eta, and you get this eta here. So when you divide by beta here, so then this square becomes this sum instead. And then what we have here is the sum over, we can replace the amplitudes by the actual Fourier coefficients if we also add the error eta. So here is the first part with the Fourier coefficients, and then we have the eta, and the eta we sum over all things where when eta has this bound, we know that the exact Fourier coefficient has to be bigger than epsilon over 2. And then when one multiply out here, we get this one times that one, which is the optimal, the sum of the Fourier amplitudes squared. And then the other terms with eta, these are small, tending to 0, asymptotically. So that's the first part of the proof. Now the other part is when the event where the Fourier coefficient happens to be large. That event has a small probability that we estimate by Chebyshev's inequality. And then one need to know, so in this step, one need to use that we need to use the Tikhonov bound. When we do the generalization error, we know that if the Tikhonov parameter is fusion of order 1, we know that the sum of the amplitude square is 1 over k. So that is needed when one do the Cauchy-Schwarz estimates here of beta, squaring this, so you obtain a sum of the squares here, and then one use one bound, and then on this one use Chebyshev's inequality, and one obtain a bound. So it is rather elementary steps, and one obtain this bound, and this bound together with that bound here, that gives the proof. That is the proof here. Okay, so let us see now. We have some numerical results which show that it works. So the delta parameter can be varied, and if it's too big, it gives results that it doesn't work well. But I mean, it is rather insensitive. When one tests the error, here we test how it converges with the number of nodes. Then it converges as one expect. Here is an improvement. I mentioned that one do a random walk. One can do a random walk with using the covariance matrix to do a adaptive random walk. Then the resampling method improves to the solid lines here with fewer iterations if one compared to the standard normal random walk, and here based on the empirical covariance matrix of the frequencies. The cutoff is rather insensitive to the cutoff. So here are the results with small enough cutoff, including epsilon 0. If you take the cutoff very big, but too big, then it matters. So clearly, so one shouldn't take it too big. But in practice, we can take epsilon 0. It looks like in our numerical tests. Let me see what else I want to show. Yeah, so I think it is time for me to stop now. So before stopping, I just mentioned that what one can do, one can also generalize to finite amount of data, and then one need an improved estimate of the generalization error for finite amount of data, which is more complicated, but that is what I gave a talk about a year ago at your conference. Anyway, this can be used in the same way as for the resampling. Okay, so I think this is it. Thank you very much.
Thank you very much for this nice talk, Anders. Any questions? Alexander.
Thank you very much for nice talk. Just, it's not really my topic, but can I see this approximation with Fourier as a high order singular value decomposition, which people in tensor community using? You see, there are some similarities between a singular value like approximation and Fourier.
Yes, in a way, when you write, if you write down the Gram matrix based on the Fourier representation, you obtain something very particular because you have the orthogonality in the Fourier representation, which you don't have in other activation functions. So that is in some way useful thinking to relate to orthogonal basis and things like that, as you mentioned. And but it has not been used in this particular reasoning, that orthogonality here. The only thing that we use about Fourier orthogonality is in the representation that we have a representation. So it has been tested with using resampling with other activation functions. So if there is such a representation, then many things of what is done can be done. But the good thing with the Fourier representation is that we know we have such a representation. Okay, so if we want to be precise about details here, so the proof, yeah. So let me go to the assumptions here. Okay, so suppose we are in high dimension then one may ask, when does the Fourier series converge pointwise? In principle, one need L bigger than D then for this to hold, if one uses Sobolev inequality and things like that. And that is actually what comes out here also. So some subtle things about Fourier are used in the proof. Anyway, yeah.
Okay, thank you very much.
Thank you. Any more questions? Okay, I think there are none. So let us thank Anders and Antoine once more for very nice talks. Then it's time for lunch. Thank you, Anders.
Tack så mycket.